This video lesson will briefly summarize the concepts of redox reactions and the activity series, taken from Chapter 4 of your textbook for AP Chemistry, Chemistry, the Central Science by Brown and LeMay. So remember from introductory chemistry that redox stands for oxidation reduction reactions, which always involve the transfer of electrons from one species to the other. And it's kind of a general rule of chemistry that electrons always have to be accounted for in redox reactions. So there are always two things occurring. One species is getting oxidized as it gives up electrons, and the other species is being reduced as it takes in electrons. The way to remember this, I think the best way, is by this saying right here, oil rig. Oil rig stands for oxidation is loss of the electron and reduction is gain of the electron. So shown in this diagram, the species on the left is oxidized as it gives up the electron to the species on the right, which is reduced. So the species on the right will then take on a less positive or more negative oxidation state. Now there are some rules to assigning oxidation states. The primary one is this, that the oxidation states of pure elements in their natural state is 0. So of course all the noble gases, but things like the Brinkelhoff, the diatomic elements, always have an oxidation state of 0. Nitrogen gas, N2, the oxidation state is 0. In addition, if you have an ionic compound, the oxidation state of the atoms in the ionic compound is equal to the charge on the ion. So shown here is aluminum bromide, aluminum with its standard, sort of most common oxidation state of 3+, and bromine is a 1-. So of course you need 3 bromines to equilibrate, if you will, the number of positive charges on the aluminum 3+. Now, for polyatomic ions, it's a little bit of a trick. The sum of the oxidation states within the polyatomic ion must equal the charge, the overall charge on the polyatomic ion. So let's do an example of this. Here's the sulfite ion, SO3 2-. So the overall charge on that polyatomic is 2-. Now, a safe assumption in most cases, with one exception that we'll talk about in a minute, is that oxygen has a 2- oxidation state. And there are 3 of them here. So if you've got 3 2- from oxygen, you're contributing 6- charges. But overall, that sulfite polyatomic ion has only a 2-. That means 4 of those 6- are being eaten up by something positive, which is the sulfur. So sulfur has an oxidation state of 4+, oxygen is an oxidation state of 2-. Let's do another quick example. Here's the sulfate ion, just to show you that oxidation states can change. Using the same math, 4 2- from oxygen is an 8-, but overall, sulfate is also the 2-. Therefore, the sulfur must be a 6+ in this case. So sulfur has the ability to change oxidation states. Let's do a couple of other ones which will introduce a sneaky concept you need to remember. Here's the dichromate. Let's do example C, dichromate ion, and then example E, which is a compound I'll introduce in just a minute. So C is the dichromate ion. And again, oxygen, let's assume it's a 2-. So overall, we're getting 7 2- or 14-, but 12 of those 14 have been used up by something. That must be the chromiums, and there are 2 chromiums making 12 pluses, so that each chromium is a chromium 6+, and each oxygen is a 2-. So overall, the charge still stays 2-. Now, example E is one you must remember for the AP exam. That is a peroxide. The peroxide polyatomic is that right here, and it has a charge of O2 2-. It is the only exception where oxygen is not an O2- charge per oxygen atom. If you look at it, it's 2 oxygens with a 2- charge. Therefore, each oxygen is an O-1. Be very, very careful there whenever you see. And typically, the AP exam has only a couple of different peroxides ever show up. One is sodium peroxide, Na2O2. Of course, hydrogen peroxide is one. And so anything in that family with sodium and hydrogen could be a peroxide. In addition, calcium peroxide, CaO2, occasionally shows up. But be very careful when you see something that has an O2 trailer on the end of it, that it is a peroxide. So if we then reveal the answers, and you can try these other ones at home, you can see that oxygen, yeah, is a 1- oxidation state, shown here. Now, this year, 2013, 2014, the AP exam no longer requires you to know about oxidizing agents or reducing agents, but there is one concept on this slide that is an important one, and that's combustion. You should remember that combustion is an oxidation reduction reaction, a redox reaction, and that's because of oxygen. Remember, the oxidation state of any pure element in its natural state is 0. And in any combustion reaction, you are having gaseous oxygen combine and form some compound. In this case, carbon dioxide and water. It's a combustion of hydrogen or a hydrocarbon. So it is changing oxidation states. And when you ever have a material changing oxidation states, then it is a redox reaction. Okay, this leads us into the idea of the activity series, and that materials can change oxidation states. Remember the copper oxide empirical formula of copper oxide laboratory that we did, the lab exercise. One of the tests for the presence of copper ion, copper 2 ion in solution, was to dunk a little piece of solid zinc into the solution and see if it was plated, if it's some material deposited on the zinc. The reaction that we were doing is shown here in a sort of macromolecular diagram, where shown on the top right, we have copper 2 ions in solution. That makes for the blue solution shown here. And we put a solid bar of zinc into that copper solution, and look what happens. A black material plates onto the zinc. The reaction that's taking place is this right here. Copper 2 ion, shown right there on the top right, and zinc solid. The zinc actually goes into solution into zinc 2+ ion, and copper is reduced. So zinc is oxidized as it gives up electrons and goes into solution in the aqueous phase, and copper is precipitated out as a solid. Copper is reduced and zinc is oxidized. So why does that occur? Well, it turns out that some metals are simply more reactive than others. And you can put this another way. Some metals are more easily oxidized than others. In this case, zinc is much more easily oxidized than copper. And so if copper ions are present in the same location or in the same aqueous field as zinc solid, zinc, being more easily oxidized, will go into solution, give up its electrons to the copper ions in solution, which are reduced and plated into the solid phase. This is the idea behind the activity series. The activity series is just a list of metals in order of decreasing ease of oxidation. So the things that are most active, the things that are most easily oxidized, are at the top of the list. And we can make some rules. Any solid metal that is higher up on the activity series can be oxidized by a metal ion below it. So if we look at an activity series, here's one right here, and we think about the reaction we just saw, copper 2 ion in solution and zinc metal. Look at the locations of those two metals. Here's zinc right here, which is more easily oxidized than copper, which is down here on the oxidation or on the activity series. So once again, any metal can be oxidized by any ion of a metal below it on the activity series. The more active metal is higher up, is more reactive. The least reactive metals are toward the bottom of the activity series. So let me erase this and go back to the slide of notes so we can write a few things down. So the more reactive metal is oxidized and goes into solution. That's the material higher up on the activity series. And it donates its electrons to the less reactive metal, which is lower down on the activity series. And the less reactive metal is then reduced from solution and appears as a solid element. So we can look at a couple of examples. Let's see if we can find one here. Let me erase a little bit. This example says, an aqueous solution of iron 2 chloride, will it oxidize magnesium metal? So here's what we're asking. We've got an aqueous solution of iron 2 chloride. So in other words, we've got iron 2 ion in solution. And we dunk a chunk of magnesium into that solution. Will a reaction occur? Well, let's go to the activity series. If we go to the activity series and we look for iron and magnesium, here again is magnesium. Iron is below it on the activity series. So the iron ions in solution will be reduced by magnesium, which will go into solution because it is the more reactive metal right here. So the answer is, yeah, this reaction will occur, and we're going to end up with magnesium 2+ ions in solution and solid iron plating out and coming out as a solid. Now, one of the other things on the activity series here that you may notice is that there is one non-metal on this list, hydrogen, right here. There's a reason for that. Will a metal displace hydrogen ion in solution is another way of asking, will a metal react with an acid? If you've got hydrogen ion in solution, that is an acid. So we can use the same rules that we've used with metals. A material that is higher up than hydrogen on the activity series will react with an acid to produce, of course, hydrogen gas and some sort of metal salt dissolved in the aqueous phase. So let's look at a couple of examples here. Hydrobromic acid is added to metallic tin. So I've shown that here. Let me isolate that right here. Hydrobromic acid, of course, the reactive species is going to be the H+ ion, and metallic tin shown right there. Well, will that react? Let's go to the activity series and check it out. There's hydrogen shown circled in red, and tin is just above it on the activity series. But the fact that it is above it means that it's more reactive and it will displace hydrogen. So hydrogen will be reduced as tin donates the electrons and goes into solution. So the answer is yes, this reaction will occur, and you're going to end up with tin, I think it's probably 2+ in solution, and hydrogen gas going out to the atmosphere. So of course this is in balance, but we're just worried about redox right now. We'll come back to redox balancing later. Some other examples. How about zinc metal added to a solution of magnesium sulfate? So essentially you've got this, if you're looking at just the ionic equation. Zinc metal added to magnesium ions. Will a reaction occur here? Well, again, we have to go to the activity series, and we have to look for those two metals. So zinc metal is right here, and what was the other one? Magnesium, I think? Let's double check. Yeah, it was magnesium. And on the activity series, magnesium is up here. So look, magnesium is more reactive. It wants to be an ion. It wants to give up its electrons. And in our example, magnesium already is an ion, so there will be no reaction here. No reaction occurs. So the higher up metal is already an ion. The magnesium, again, back to this slide, is higher up on the activity series. All right, let's look at one more example here. Aluminum metal is added to a solution of cobalt sulfate. I think you get the idea right now, but let's look for aluminum metal right here added to a solution of cobalt sulfate, and cobalt sulfate then is CO2+. So this is the metal ion in solution. This is more reactive. So it's true that this will displace, aluminum will displace cobalt ion in solution. Aluminum will go to the 3+ oxidation state, and cobalt will be reduced and will plate out of solution. So in this case, we're going to have, again, balancing is going to be an issue here, but we're going to ignore it for now. Aluminum will go into the aqueous phase, and cobalt solid will be reduced.